This video will introduce you to the world of semiconductors. You will learn about the N materials and P materials. You will see how they are formed and how they function in solid-state devices. You will also learn about the depletion region in a semiconductor device, and you will see that by controlling the depletion region, you can control the device. Next, you will study many of the more common solid-state devices to gain a better understanding of semiconductor theory. You will see how these devices actually work. You're watching a listing of some of those devices to be covered in this video. Finally, you will see how many of today's integrated circuits are manufactured using a technique called monolithic fabrication. To gain a better understanding of semiconductor theory, we must first examine the atom. Here we see a silicon atom. As you may have noticed, the outermost ring of electrons are contained in an electrostatic force called the valence shell. In a pure silicon atom, the valence shell will contain only 4 electrons. The most electrons which may exist in the valence shell are 8. The closer the electrons are to the nucleus, the stronger the forces are that bond the two together. Therefore, each shell of electrons will have an associated energy level that will represent the amount of energy required to remove an electron from the shell. Since the electrons in the valence shell are the furthest from the nucleus, they will require the least amount of energy to become displaced from the atom. When atoms are combined to form a solid material, the electrons in the valence shell of each atom will be influenced by the forces created from the neighboring atoms. As these atoms merge, energy levels are created within the atomic structure of the material. In any given material, there are 2 distinct energy bands in which the electrons may exist. These are the valence band and the conduction band. Separating these 2 energy bands is a third band in which electrons do not normally exist. This band is termed the forbidden gap. The electrons in the conducting band are those which have been displaced from the valence band. These electrons are easily moved within the material with only small amounts of energy being applied. The electrons contained in the valence band, on the other hand, will require a much larger amount of energy to become extracted from the valence band and forced into the conduction band. Depending upon the type of material which the combined atoms form, the forbidden gap may be large, small, or non-existent. The difference between insulators, conductors, and semiconductor materials will depend upon the size of the forbidden gap within the materials. To gain a better understanding of this, we will first examine insulator materials. As you may have noticed, the insulator has a large, wide forbidden gap. Therefore, it will require large amounts of energy to displace the electrons from the valence band. For this reason, insulating materials make very poor conductors. Conductors, on the other hand, have no forbidden gap at all. The conduction and valence energy bands will actually overlap. Therefore, only small amounts of energy are required to move the valence electrons through the material. Conductors normally have very large numbers of electrons available for conduction. As you can see here, semiconductor materials have a much narrower forbidden gap than did the insulator materials just discussed. Therefore, the semiconductor material will require much less energy to extract the electrons from the valence band. But in the same respect, the semiconductor material will require more energy to displace these electrons than would be required by conductor materials. As a rule of thumb, elements with 5 or more electrons in the valence shell are considered electrical insulators. Elements with 4 electrons in the valence shell are considered intrinsic semiconductor material. And elements with 3 or less electrons in the valence shell are considered conductors. Silicon and germanium are the 2 most common semiconductor materials used in solid-state devices. The atoms contained in any solid material are held together by a force referred to as a bond. There are 3 kinds of atomic bonds. These are ionic, metallic, and covalent. Insulators are formed with ionic bonds. Insulators will contain both positive ions and negative ions, which create a strong electrostatic force of attraction between the atoms. It is this electrostatic force which bonds or holds the material together. The term ionic bond is used because the atoms are ionized. Metallic bonding occurs in materials which are used for conductors. As you learned earlier, conductors contain a large number of electrons which are available for conduction. As the electrons leave the valence ring of the atoms within the material, the atoms become positively charged and therefore become positive ions. A strong electrostatic force will exist between each atom and the many free electrons. It is this strong electrostatic force between the atoms and free electrons which forms the actual bonding of the material. Covalent bonding occurs in materials which are used for semiconductors. Covalent bonding holds the atoms much closer together than does the ionic or metallic bonds. Semiconductor materials contain both positive and negative ions. The positive ion will contain holes in which electrons could exist, while the negative ion contains extra electrons. Since the atoms are held closer together, the valence shell in each atom will share electrons with the neighboring atoms. This results in a strong covalent bonding action between the atoms. This sharing of electrons causes the atom to act as if each atom had 8 electrons in their valence shells. This in turn causes the material to act as an insulator. Silicon and germanium in their pure form are referred to as intrinsic materials. Before these materials can be used as a form of semiconductor material, they must have impurities added to them so the material can conduct an electric current. The process of adding impurities to the intrinsic material is referred to as doping. There are 2 classifications of impurities used for doping. These are trivalent and pentavalent. Trivalent elements will contain only 3 electrons in the valence shell, whereas pentavalent elements will contain 5 electrons in the valence shell. Common pentavalent impurities include such agents as arsenic, antimony, bismuth, and phosphorus. When a pentavalent impurity is added to the intrinsic material, it causes an extra electron to be generated, because when the covalent bond forms the 2 elements together, there can be only 8 electrons in the valence shell. Since the pentavalent impurities have 5 electrons and the intrinsic materials have 4 electrons, when the 2 are combined, there is an extra free electron produced. This free electron is termed a donor. Since the electron has a negative charge, the crystalline structure which was formed by the covalent bonding is called an N-type material. When a voltage is applied to the N-type material, the electrons will flow with only a small amount of energy being applied. Common trivalent impurities include such agents as aluminum, indium, gallium, and boron. Trivalent impurities contain only 3 electrons in the valence shell. This creates a vacancy or hole when the crystalline structure is formed. Since this hole can accept an electron, it is called an acceptor. Intrinsic materials which are doped with trivalent impurities are referred to as p-type semiconductor materials. When a voltage is applied to a p-type semiconductor material, the holes will flow from the positive potential to the negative potential. This is known as hole flow and is only possible in p-type semiconductor materials. We will stop now for a short review of the material covered to this point. The maximum electrons which may exist in the valence shell of any atom is 8. The valence shell of the silicon and germanium atom will contain only 4 electrons. The closer the electrons are to the nucleus, the stronger the forces are that bond them together. Since the electrons in the valence shell are furthest from the nucleus, they require the least amount of energy to become displaced from the atom. 2 distinct energy bands exist in any material. They are the valence band and the conduction band. A third band may exist which separates these energy bands. This band is termed the forbidden gap. Insulators, as you have seen, will have a wide forbidden gap. Conductors will have no forbidden gap at all. Their energy bands will actually overlap. Semiconductor materials, on the other hand, will contain a narrow forbidden gap. There are three kinds of atomic bonds: ionic, metallic, and covalent. Insulating materials are formed with ionic bonds. Conductors are formed with metallic bonds. And semiconductor materials are formed with covalent bonds. Pure silicon and germanium are referred to as intrinsic materials. Intrinsic materials must be doped with impurities to allow the material to conduct an electric current. The two basic types of impurities used for doping are trivalent and pentavalent. Trivalent impurities contain 3 electrons in their valence shell. Pentavalent impurities contain 5 electrons in their valence shell. Trivalent impurities are used to form p-type semiconductor materials. Pentavalent impurities are used to form n-type semiconductor materials. This concludes our first review. Next, we shall examine some of the more common single-junction semiconductor devices. A semiconductor diode will consist of both p-type and n-type semiconductor materials which are joined together. Here we see the schematic symbol of a general-purpose diode. As you may have noticed, the p material forms the anode and the n material forms the cathode. Where the two materials are joined is called the p-n junction. When the p-n junction is formed, some of the donor electrons will drift across the junction into the p material, leaving positive ions in the n material. As the electrons drift into the p material, it creates a negative potential which repels any further drifting of the free electrons. The positive ions in the n material create a positive potential which will repel any drifting of the holes into the n material. This small area where the drifting of the electrons and holes have occurred will form a new area within the semiconductor material. This area is termed the depletion region. The depletion region will have an equal number of positive ions on one side and negative ions on the other side. The depletion region forms a barrier which must be overcome before current can flow through the semiconductor device. For silicon-type semiconductor devices, this barrier requires a voltage of 0.7 of 1 volt before current can flow. And for germanium-type semiconductor devices, this barrier requires a voltage of 0.3 of 1 volt. It is this depletion region which makes it possible to control the semiconductor device. Semiconductor materials have majority and minority charge carriers. The majority charge carrier in the p-type material is the hole, while the minority charge carrier is the electron. The majority charge carrier in the n-type material is the electron, and the minority charge carrier is the hole. When any semiconductor device is used in a circuit, it will have a wide range of voltages being applied to it. These voltages are referred to as bias voltages. The bias voltage will determine how the device will react in the circuit. When a negative bias voltage is applied to the p side of the semiconductor and a positive bias is applied to the n side of the device, it causes the majority charge carriers to move away from the p-n junction. This in turn causes the depletion region within the device to widen. When the depletion region widens sufficiently, it will cause the majority charge carriers to stop flowing. This is referred to as a reverse bias condition. As you will learn later in this program, there are certain semiconductor devices that are designed to operate in the reverse bias mode. Within any semiconductor device, there will be a reverse current flow made up of minority charge carriers. As you learned earlier, the minority charge carrier in the p material is the electron, and the minority charge carrier in the n material is the hole. This reverse current is usually very small. It is typically about 1 microampere for silicon-type devices and approximately 10 microampere for the germanium-type devices. These values are based on a room temperature condition of 70 degrees Fahrenheit. There is, however, a limit to the amount of reverse current which may be applied to the p-n junction. This limit is termed the reverse breakdown voltage. This voltage may range from a few volts to several thousand volts. When the reverse breakdown voltage is reached, the reverse current will increase at a rapid rate, which usually results in the device being destroyed. When a positive bias is applied to the P material and a negative bias is applied to the N material of the semiconductor device, it causes the majority charge carriers to flow toward the p-n junction. This is referred to as a forward biased p-n junction. If enough bias voltage is applied to the device, it will cause the depletion region to disappear and allow current to flow through the device. The negative bias on the N material will attract the holes in the P material and at the same time repel the electrons toward the p-n junction. In the same respect, the positive bias on the P material will repel the holes toward the p-n junction and attract the free electrons toward the positive bias. As the temperature is increased in a semiconductor material, both the electrons and holes will flow more easily through the material. This is due to the thermal agitation of the atoms, which increases the conductivity of the material. As the temperature increases, so will the forward and reverse current flow through the p-n junction. Germanium devices are more sensitive to temperature changes than our silicon devices. The reverse current for both devices will be about double for every 10 degrees Fahrenheit increase in temperature. Since the current flows through a semiconductor increases as the temperature increases, it is said to have a negative temperature coefficient. The negative temperature coefficient will usually have a destructive effect on the semiconductor device. As the semiconductor passes current, it generates heat due to the electrons colliding with one another during the normal current flow. The greater the current flow, the more the electrons are agitated. This in turn creates more heat, which causes the device to further increase the conductivity of the material. This will continue until the maximum forward or reverse current rating is exceeded. When the maximum current rating is exceeded, it usually destroys the device. This phenomenon is referred to as thermal runaway. Transistors are more susceptible to this effect than our diodes. Now that you have an understanding of how the p-n junction works, we will examine some of the more common special purpose diodes which you will encounter as a technician. You have already seen that when an ordinary general purpose diode is reverse biased, it will have a very small reverse current flow which is made up of minority charge carriers. If this reverse bias voltage is increased sufficiently, the p-n junction will break down and a large reverse current will flow. This usually destroys the device. However, there is a special purpose diode that is designed to operate in the reverse bias mode. This diode is referred to as a Zener diode. The Zener diode is designed to operate at a specific breakdown voltage when reverse biased. This breakdown voltage is called the Zener breakdown or avalanche breakdown voltage. When the reverse bias voltage of the Zener is reached, the diode will break down and a very heavy reverse current will flow through the device. If this reverse current flow is not restricted by a resistor or some similar device, the Zener would be destroyed by the excessive current. Therefore, when Zener diodes are operated in the reverse bias mode, there must be a current limiting device in series with the Zener to keep it from self-destructing. The current limiting device is usually a resistor. The value of the resistor is chosen so that the Zener will operate between its threshold current and the maximum Zener current. Once the Zener avalanche is on, the voltage drop across the Zener will not change. Even if more current is passed through the device, this makes the Zener diode an excellent voltage regulating device. When the reverse bias is reduced below the avalanche voltage, the current will return to its off-state condition. When the Zener is forward biased, it acts as an ordinary diode. Therefore, the Zener is usually operated in its reverse bias mode. The next semiconductor device we shall examine is the tunnel diode. The The semiconductor material in the tunnel diode is doped extremely heavily with impurities. This gives the tunnel diode a very narrow depletion region. As seen on this graph, the tunnel diode has a very fast response to input voltages. These devices are used almost exclusively in high-frequency circuits. Tunnel diodes may be used as amplifiers, oscillators, or as switching devices. Because of the fast response time of the tunnel diode, it requires a smaller bias voltage and a lower load resistance than do most other semiconductor devices. Tunnel diodes are designed to operate in the frequency range of 300 to 400 megahertz. The tunnel diode has a negative resistance region. In this region, the current is inversely proportional to the voltage. An increase in voltage will result in a decrease in current. Because the depletion region in the tunnel diode is very narrow, it does not constitute much of a barrier to the electron flow. A small forward bias will cause the majority charge carriers to cross the depletion region. When this occurs, the majority charge carriers are said to be tunneling through the barrier. When the tunnel diode is reverse biased, the majority charge carriers will tunnel through the barrier despite the fact that the junction is reverse biased and a substantial current will flow. The reverse characteristics of the tunnel diode is linear, like that of a resistor. When the tunnel diode is forward biased, its initial behavior is similar to its reverse bias condition. As you can see from this characteristic curve, when the forward bias is increased, more and more electrons will tunnel through the barrier, thus increasing the current. This occurs until a maximum level of tunneling is reached. As the forward bias is further increased, the tunneling effect will begin to decrease. When the forward bias is increased sufficiently, the tunnel diode characteristics will become similar to that of an ordinary diode. The tunnel diode is generally operated in its negative resistance region between the peak current and the valley current. The negative resistance region is its most important property. Here we see the Shockley diode. It is constructed of 4 layers of semiconductor material. This device is commonly used in relaxation oscillator circuits and in triggering circuits for silicon-controlled rectifiers. The Shockley diode is basically a low-current SCR without a gate. You will learn about the SCR later in this program. The Shockley diode is turned on when the anode to cathode voltage is increased to the forward switching voltage. The minimum current at which the Shockley diode will stay on is referred to as the hold current. When the current drops below this level, the diode will no longer conduct. Since the Shockley diode is a 4-layer device, it will have 3 PN junctions. 2 of the junctions will be forward biased and the third will be reverse biased. When the diode is forward biased, junctions 1 and 3 will become forward biased and junction 2 will become reverse biased. The reverse bias on the second junction will limit the current flow to minority charge carriers. Once the diode's forward bias voltage is increased to the reverse breakdown voltage of the second junction, the diode will turn on. When the diode turns on, its resistance will drop from several thousand ohms to a few hundred ohms. Here we see the Shockley diode being used in an oscillator circuit. When the circuit is energized, capacitor C1 will charge from the supply until the capacitor voltage reaches the diode's switching voltage. The diode then turns on and conducts a current flow which discharges capacitor C1. When the voltage on the capacitor falls below the level required to keep the diode on, the diode will turn off and allow the capacitor to charge back up. The output voltage will be a sawtooth waveform. Resistor R1 must be small enough to allow the diode's switching current to flow when the diode switches on. Here we see the LED or light-emitting diode. It is made from gallium phosphide, gallium arsenide, and gallium arsenide phosphide. The gallium phosphide will emit a red or green emission. The gallium arsenide will emit an infrared radiation, and the gallium arsenide phosphide will emit a red or yellow emission. When the electrons from the N material cross the junction of a forward-biased LED, they combine with the holes in the P material. This carrier recombination of charge carriers causes the LED to radiate energy in the form of light. Since the PN material is encased in a transparent casing, the PN junction becomes the light source. The relatively large amounts of current consumed by the LED are their only major disadvantage. Apart from this, the LED does have the advantage of long life and ruggedness. Here we see the varactor diode. The VVC diode is also referred to as a voltage variable capacitor, or varicap for short. Basically, the varactor diode is a reverse bias diode, and its capacitance is that of the PN junction depletion region. As you recall, a large reverse bias produces a wide depletion region. This depletion region will act as a dielectric between two conducting plates, which is the case would be the two semiconductor materials. Because of this characteristic, the varactor diode has the ability to act as a voltage variable capacitor. The primary application of the varactor diode is as a tuning device for oscillator circuits. When the diode is reverse biased, the depletion region will become depleted of majority charge carriers, which causes the depletion region to become a poor conductor. This depletion region then acts as a dielectric material. The width of the depletion region will be proportional to the applied voltage. Therefore, the capacitance of the varactor diode will be inversely proportional to the applied voltage. Before examining more complex semiconductor devices, we will quickly review the material on the diodes just discussed. A semiconductor diode will contain both an N material and a P material. The area at which the two materials are joined is termed the PN junction. When the two types of semiconductor materials are bonded together, a depletion region is formed. The depletion region will have a deficiency of majority charge carriers. When the diode is forward biased, the majority charge carriers are pushed toward the PN junction, which in turn reduces the depletion region. When the diode is reverse biased, the majority charge carriers are pulled away from the PN junction, thereby increasing the size of the depletion region. The Zener diode is designed to operate in its reverse bias condition. The Zener must have some form of resistance in series between it and the power source, or the device could become destroyed. Tunnel diodes have a very narrow depletion region. This causes the device to have a very fast response to input signals. Tunnel diodes may be operated in either their reverse or forward bias conditions. The Shockley diode is a four-layer device that is commonly used in oscillator and triggering circuits. Light-emitting diodes are made from gallium phosphide, gallium arsenide, or gallium arsenide phosphide. The recombination of the majority charge carriers causes the LED to give off energy in the form of light. The varactor diode is used as a voltage variable capacitor. Varactors are normally operated in the reverse bias mode, and its capacitance is that of the depletion region. This completes review number 2. Next we shall examine some common amplifying and switching devices. Here we see a bipolar junction transistor, or BJT for short. As you notice, this transistor is a three-layer device. Depending on how the semiconductor materials were formed, the bipolar junction transistor may be either an NPN or a PNP type device. In either case, there will be three leads attached to the device. One will be the emitter, one will be the base, and one will be the collector. The emitter lead is easily identified by the arrow placed on it. As you notice, the arrow points in on the PNP, and it points out on the NPN transistor. The base section of the transistor is very narrow and is very lightly doped. The emitter and collector sections, on the other hand, are doped very heavily. This causes the depletion regions between the emitter base and the collector base to penetrate very deep into the base section of the transistor. Since the base section is lightly doped, there will be fewer majority charge carriers available to recombine with the charge carriers coming from the emitter section. As a result, about 95% of the emitter's charge carriers will pass through the base section and flow into the collector of the device. Transistors are considered current amplifying devices. This is due to the fact that a small base current can control a much larger collector current. When the transistor is biased properly, the emitter-base section will be forward biased. This causes the emitter-base junction to have a much narrower depletion region. The collector-base junction, on the other hand, will become reverse biased, which will widen its depletion region. Since the base section is lightly doped and the collector section is heavily doped, the collector-base depletion region will extend deep into the base area. When the majority charge carriers from the emitter flow into the narrow base section, they become minority charge carriers. The reverse bias junction between the collector and base will enhance the flow of these minority carriers. The reverse bias then carries the minority carriers into the collector section. Since the transistor is a three-terminal device, one of the terminals must be connected so it is common to both the input and the output of the device. Therefore, the bipolar junction transistor may be connected in a circuit in one of three ways. It may be connected in a common emitter configuration, a common collector configuration, or as a common base configuration. Each of these configurations will have its own circuit characteristics. The common emitter will have a typical input impedance of 1500 ohms. The output impedance will usually be around 1 megohm. The voltage gain will generally be about 330 with a current gain of 50. This gives the common emitter a power gain of 16,500. You will also notice that the circuit inverts the phase of the incoming signal by 180 degrees. The common emitter is the most widely used of the three configurations. The common collector, which is also referred to as an emitter follower circuit, has a typical input impedance of approximately 52,000 ohms. The output impedance of this circuit is usually very low, somewhere around 80 ohms. The common collector also provides a current gain of about 50 and a power gain of about 50. However, this circuit provides no voltage gain. The common collector is generally used as a buffer amplifier. You may also have noticed that this circuit does not invert the incoming signal. The common base circuit, on the other hand, will have a typical voltage gain of 327 and a current gain of less than 1. This gives the common base a power gain of approximately 320. The input impedance of this circuit is about 30 ohms, and the output impedance will be about 1 megohm. The common base is normally used for very high frequency voltage amplification situations. Here we see the junction field effect transistor. You will often hear this device being referred to as simply a JFET. The junction field effect transistor is constructed of a bar section of one type of semiconductor material sandwiched between two sections of the other type of material. As you may have noticed, the JFET is also a three-terminal device. It has a gate, drain, and source lead. The junction field effect transistor is a voltage-operated device. The JFET transistor requires virtually no input current. This gives it an extremely high input impedance. There are two types of JFET devices, N-channel and P-channel. The bar of semiconductor material placed between gates of the device is referred to as the channel. The ends of the channel are designated as the drain and source. The channel of the transistor is more lightly doped than is the gate sections. This causes the depletion region to penetrate deep into the channel when the device is reverse biased. Since the depletion region is depleted of majority charge carriers, it behaves as an insulator. When the reverse bias is increased, the channel through which the charge carriers flow is made more narrow. This results in an increase of the effective resistance of the JFET device. When the reverse bias is increased sufficiently, the depletion region meets at the center of the channel and cuts off the current flow through the device. This is referred to as the pinch-off region. The gate channel junctions are almost never forward biased. The name field effect comes from the fact that the depletion regions in the channel are the result of the electrostatic field caused by the reverse bias gate channel junctions. If a bias voltage is not applied to the gate of the device, the current will flow through the transistor as if it were flowing through a resistor. When the gate of the junction field effect transistor is reverse biased, the only current which will flow into the gate sections is the reverse current flow, which consists of the minority charge carriers. Therefore, the gates of the JFET will draw virtually no current. Amplification of the JFET is made possible by increasing or decreasing the gate voltage. The corresponding drain current will vary accordingly to produce an amplified reproduction of the input signal being applied at the gate of the device. Unlike the bipolar junction transistor, the JFET must be biased to stop the current flow through the device. In this respect, the junction field effect transistor operates much like a vacuum tube. Here we see a MOSFET device. MOSFET stands for metal oxide semiconductor field effect transistor. There are many types of MOSFET devices. Here we see another type of MOSFET device. As you may have noticed, this device has an insulated material placed between the gates and the channel material. This device is commonly referred to as an insulated gate metal oxide semiconductor field effect transistor. Let's examine how the MOSFET device is constructed. To construct a MOSFET device, you must start with a P-type or N-type intrinsic material. Next, two blocks of heavily doped semiconductor material are diffused into the solid block. Then the surface is coated with a layer of silicon oxide. There are two holes left in the oxide layer to make contact with the heavily doped semiconductor blocks. If we were using an N-type semiconductor material, then the heavily doped blocks would be P-type, or if we were using P-type semiconductor material, the blocks would be N-type material. Next, metal is deposited through the holes to form the drain and source terminals. Then a metal plate is deposited on the silicon oxide between the drain and source terminals. This plate will become the gate of the MOSFET. The silicon oxide is being used as an insulator. Since the gate is placed on the silicon oxide, the gate will become insulated from the channel of the MOSFET. In our example, we used a P-type substrate with N-type blocks. If the drain is made positive with respect to the source and no bias is applied to the gate, there will be very little current flowing between these 2 points. This will be due to the fact that the MOSFET will be in a forward and reverse bias condition. Therefore, the only current flow will be from minority charge carriers. When the gate terminal is made positive with respect to the source terminal, negative charge carriers will be induced into the channel between the drain and source. As the positive bias on the gate is increased, more negative charge carriers will be induced into the channel. These induced charge carriers will actually be minority charge carriers within the semiconductor material. These charge carriers will be attracted to the positive voltage being applied to the gate terminal and will form a channel across the surface of the insulated material beneath the gate plate. The higher the bias voltage applied to the gate, the wider this channel of minority charge carriers will become. Since the conductivity of the channel is enhanced by the positive bias being applied to the gate of the device, this type of semiconductor is known as an enhancement mode MOSFET. Because the gate is insulated from the channel, there will be virtually no current flow between the substrate channel and the gate. This gives the insulated gate MOSFET a very high input impedance. Next, we shall look at the depletion mode insulated gate MOSFET. As you can see, it is very similar to the enhancement mode MOSFET. The primary difference being that this device has a lightly doped channel placed between the two heavily doped source and drain blocks. You should also have noticed that this channel is made of the same type of material as is used to form the source and drain blocks. If the drain is made positive with respect to the source and no bias is applied to the gate, a current will flow through the channel. Now, suppose we make the gate negative with respect to the P material. We see that the positive charge carriers will be induced into the lightly doped channel that was placed between the source and drain. These positive charge carriers will absorb the negative charge carriers in the N channel and cause the channel's resistance to increase. You may also have noticed that the charge carriers were pushed toward the bottom of the channel. If the negative bias on the gate is sufficiently increased, it will cause the channel to stop the current flow between the source and drain. The gate is then said to have depleted the charge carriers from the channel. Now suppose we make the gate positive with respect to the P material. This causes the charge carriers to become induced into the channel. This will decrease the resistance of the channel and allow more current to flow between the source and drain terminals. As you can see, this device can be operated either in the depletion or enhancement mode of operation. Let's pause at this point for another review of the material just discussed. There are two types of bipolar junction transistors, the NPN and PNP. Each will have three terminals, one being the emitter, the second being the base, and the third being the collector. BJTs are considered current amplifying devices because the base must draw current to allow the device to turn on. Approximately 95% of the majority charge carriers which leave the emitter will travel through the base section and flow into the collector of the device. BJTs are commonly found in one of three configurations: in the common emitter, common collector, or in the common base configuration. Of these, the common emitter is the most frequently used. The junction field effect transistor is another common three-terminal device. JFETs are available in both N-channel and P-channel devices. The three terminals on the junction field effect transistor are labeled the drain, gate, and the source. Since the JFET controls the current flow between the drain and source by means of an electrostatic field, it draws very little gate current. Therefore, the JFET is considered a voltage amplifying device. MOSFETs, on the other hand, draw virtually no gate current because of the thin layer of silicon oxide placed between the gate terminal and the substrate material. MOSFETs may be operated in either the enhancement or depletion modes of operation. Now to continue with the program. Here we see a silicon control rectifier, or SCR for short. The SCR is very similar to a standard diode except for one major advantage. It is controlled to a certain extent by a gate current. As you may have noticed, the construction of the SCR is very similar to that of the Shockley diode, the only exception being that the SCR has a gate terminal connected to the P section nearest the cathode. When a positive voltage is applied at the gate of the device, the gate cathode junction will become forward biased. This allows the SCR to turn on. Once the SCR turns on, it will remain on even if the gate signal is removed. When the SCR turns on, it reacts much like a regular forward biased diode. The SCR will remain on as long as the current flowing through the device remains above its latch-on current level. When the SCR drops below this level, it turns back off. For this reason, the SCR is most commonly used in AC circuits. Like the diode, the SCR can conduct current in only one direction. The ability of the SCR to remain on even after the triggering signal has been removed is referred to as latching. The SCR requires only a brief pulse of gate current to turn the device on. Once on, the gate has no further control. The gate, however, can be used to keep the SCR from turning on, or it can be used to turn the SCR on at any point in the forward half cycle of a sinusoidal input. This makes the SCR very useful in controlling many AC-powered devices. SCRs are commonly used as current control devices in servo systems. Here we see the triac. The triac is essentially two inverse parallel connected SCRs with a common gate. This allows the triac to conduct current in both the positive and negative directions. Let's briefly look at the operation of the triac. With a positive voltage being applied at terminal A2 with respect to A1, and with a positive bias voltage applied at the gate, the PN junction between P2 and N4 will become forward biased. At the same time, the PN junction between P2 and N2 will become reverse biased. Therefore, the current flow through the N2 section will be due to minority charge carriers. The PN junction between N2 and P1 will then become forward biased and allow the current to flow from terminal A1 to A2. The current will continue to flow until the device drops below the holding current level. Now suppose we make A2 negative with respect to A1, and the gate is pulsed with a negative signal. The PN junction between N3 and P3 will become forward biased. At the same time, the p-n junction between N3 and P2 will become reverse biased. As this occurs, the p-n junction between P2 and N1 will become forward biased and allow the minority charge carriers to be pulled through the N3 section. After the minority charge carriers have flowed through the N3 section, they will easily pass through the forward bias junction of P2 and N1 and cause the triac to turn on in the opposite direction. The gate lead on the triac is used to control the direction of current flow and the point of sine wave at which the device will start conducting current. The triac is very useful in controlling AC loads in which rectification is not desired. Here we see the diac. It is similar to the triac in that it can conduct an AC current in both directions. As you may have noticed, the diac is a 3-layer semiconductor device with equal doping in both N layers. As an AC voltage develops across the device, it reaches an avalanche point and breaks into conduction. The avalanche point is typically between 25 to 35 volts in either direction. Diacs are commonly used for delaying the firing of SCRs, or in some cases triacs, until the voltage rises to about 30 volts. Here we see the unijunction transistor. You will often hear this device being referred to as simply a UJT. Even though the UJT is a 3-terminal device, its operation is quite different from that of the BJT or FET transistors. It works like a voltage-controlled switch and does not amplify. The 3 leads on the unijunction transistor are called the base 1, base 2, and the emitter. The emitter section of the unijunction transistor has a resistance which rapidly decreases when the input voltage reaches a certain magnitude. This is referred to as a negative resistance characteristic. It is this characteristic that makes the UJT useful in timing and oscillator circuits. The unijunction transistor is constructed of a bar of lightly doped N-type silicon with a small piece of heavily doped P-type material attached to one side. Since the silicon bar is lightly doped, it has a very high resistance. When a positive bias voltage is applied to the emitter, the p-n junction becomes forward biased and current will flow through the p-n junction. This causes the resistance of the N-type bar material to decrease. With the decrease in resistance, the voltage drop across the emitter base 1 junction also decreases, which in turn causes the p-n junction to become more heavily biased. As the p-n junction is biased even further, it causes a greater forward current flow, which further reduces the resistance of the bar material. When the UJT is operating in this mode, it is operating in its negative resistance region. The negative resistance region is the normal operating mode of the UJT. Here we see the unijunction transistor in a relaxation oscillator circuit. When the circuit is energized, the capacitor charges through the resistor to the positive side of the power source. When the capacitor voltage reaches the peak voltage level of the UJT, the device fires and rapidly discharges the capacitor. Once the capacitor has discharged, the unijunction transistor turns back off and allows the capacitor to charge back to the positive side of the power source. This process will continue indefinitely. The resulting output will be a sawtooth waveform. The frequency of the oscillator circuit will be controlled by the values of the resistor and capacitor. Here we see the phototransistor. All transistors are light sensitive, and phototransistors are specifically designed to take advantage of this important characteristic. The most common phototransistor is the NPN junction transistor with a large exposed base area. The base area is usually exposed to light through a lens placed at the top of the transistor housing. The light energy entering the base area will replace the base emitter current required in the ordinary bipolar junction transistor. The collector current will increase with the intensity of the light source due to the amplification factor of the transistor. Remember, the BJT is a current amplifying device. The phototransistor may or may not have a base lead. Phototransistors are widely used as photodetectors for such devices as day-night switches, alarm systems, punch tape readout devices, or any type of circuit which requires the use of some form of light energy to activate the system. Phototransistors are more light sensitive than are photodiodes. However, photodiodes have the fastest switching time of the two. Photodiodes have a typical switching time of nanoseconds compared to the switching time of microseconds for the phototransistor. Here we see an optical coupler. The optical coupler is simply a phototransistor and light-emitting diode combined in a single IC package. When current flows in the diode side of the device, the emitted light is directed toward the phototransistor's base area, which causes current to flow in the transistor. Since the coupling between the LED and phototransistor is purely optical, there is a high degree of electrical isolation. This makes the optical coupler ideal for such applications as combining TTL circuits with CMOS circuits. The coupler may be operated as a switch or in a linear mode. When operated as a switch, both the LED and phototransistor are normally in their off condition. A pulse of current through the LED will cause the phototransistor to switch on for the duration of the pulse. Operation in the linear mode is made possible by biasing the LED at the midpoint between its cutoff point and saturation. As the input signal going into the LED varies, it causes the brightness of the LED to increase and decrease accordingly. The phototransistor detects this variation of light and produces an amplified reproduction of the input signal. Now that you have seen how various semiconductor devices operate, we will examine a simple integrated circuit. Integrated circuits are nothing more than a combination of interconnected circuit elements designed to perform a given task. The integrated circuit provides many advantages, some of which are smaller packaging, increased reliability, reduced power consumption, and lower cost. A method referred to as monolithic fabrication is used to mass produce many of today's ICs. In the monolithic fabrication technique, all of the components are fabricated by placing a very thin and highly polished silicon wafer in an oven at a high temperature and exposing it to an atmosphere of semiconductor impurities. This process is called the diffusion method. After the wafer is placed into the heated oven, oxygen is induced into the oven chamber and a thin coating of silicon dioxide is formed on the wafer. The silicon dioxide acts as an insulator. The surface of the wafer is then coated with a photosensitive emulsion. Next, a mask is placed over the wafer. The components of the IC are designed into the mask. The mask is designed to cover part of the wafer while leaving other parts of the wafer uncovered so the semiconductor impurities can diffuse into the silicon wafer. Next, the wafer is exposed to ultraviolet light. Then the wafer goes through a developing process which hardens the areas not exposed to the ultraviolet light. The exposed areas of the silicon dioxide are then etched away by hydrofluoric acid. The silicon dioxide which was not etched away represents the locations of the transistors and other components of the integrated circuit. The layer of N material not covered by the silicon dioxide is then exposed by the diffusion process to P-type impurities. This changes the uncovered N-type material into P-type material. Next, another silicon dioxide film is formed on the surface of the wafer. The surface of the wafer is once again coated with a photosensitive emulsion and a second mask is placed onto the wafer. After the second mask is in place, the wafer is exposed to ultraviolet light. The wafer then goes through another developing process which hardens the areas not exposed to the light. Once again, the areas which were exposed to the light are etched away. The part of the wafer not covered by the silicon dioxide is then exposed to more P-type impurities. This same process is repeated as many times as necessary to build the desired circuit. Finally, the holes are etched through the last silicon dioxide layer to form connections to the component parts. A thin film of aluminum is patterned to form point-to-point contacts for the circuit components. Here we see the final integrated circuit with an equivalent schematic drawing of the IC. This was just an example of how an IC is formed using the monolithic fabrication technique. By now, you should have a good solid understanding of semiconductor theory and how many of the more common devices function. To gain the most from this video, it is recommended that you view it many times over. A good technician must have a thorough understanding of how semiconductor devices operate to troubleshoot and repair today's complicated electronic equipment.